So we'll finish up our discussion on chromatic dispersion. So last class we discussed waveguide dispersion and saw how it can be used to sort of tailor the dispersion of optical fibers depending on our exact application. We can tune the, for example, the zero dispersion wavelength, right? So just to summarize, look at a plot here of dispersion of various different types of fibers. Okay, so again on the y-axis we are plotting dispersion in picosecond per nanometer per kilometer. Okay, and this is the total dispersion, material plus waveguide. Okay, so yeah, so let's mark the x-axis, wavelength. Okay, so again, so conventional, the standard single mode fiber, the zero dispersion wavelength occurs around 1.3, right, 1310 to 1330 nanometers, somewhere there. So that looks like this. Right, so this is what we call the conventional single mode fiber, or the standard single mode step index fiber, like SMF 2080 that we discussed, right? So this has a refractive index profile like that, right? So again, this refractive index contrast is about 0.35%, the core diameter is about 9 micron. Right, and then at the end of last class, we also discussed, so for example, you want to work at 1.55 micron, right, which is the lowest loss wavelength for silica fibers, but the dispersion for the conventional fiber is high compared to, let's say, 1.3 micron. So we can use a different pore size and index contrast, right, again to modify the waveguide dispersion and hence the total dispersion. Right? So that was a dispersion shifted fiber, right, where it would shift the zero crossing to above 1.5 micron. Okay, so this is the dispersion shifted fiber. Right, so this has a smaller core. So diameter here is about 4.4 micron, and larger index contrast, so about more than 1%. Right, and again, so recall that the waveguide dispersion went something like, so it depended on this index contrast, and then some function of the n. Right, so basically we will increase the index contrast, so the waveguide dispersion becomes more negative, so the overall dispersion shifts down. Okay, hence the zero crossing. Okay, then we can have even more fancy types of fibers for even more tailored kind of dispersion profiles, right? So one thing one can do, so for example, most of the global fiber optic network which was laid down was this conventional single mode fiber, right? As you saw, so the SMF28 is the most widely deployed fiber in the world, right? So we already have these fibers laid down. So to replace, for example, all of them by this dispersion shifted fiber would not be economically viable, right? So now, how do we use these fibers at 1.55 micron for long transmission links, right? So what you can do is, so this positive dispersion or the anomalous dispersion that you have here for the conventional fiber, so at the receiver end, you can just put some length of fiber which has the opposite dispersion, okay, and then choose the length such that basically you cancel out the broadening or the chirping that you get from this by an opposite chirping due to that. Okay, so as we saw, the broadening and the chirping scales with the dispersion coefficient times the length, right? So again, you see here, if I further increase this index contrast, then I can further shift the waveguide dispersion down, and I can do it if I really make this big enough. Okay, then I can make it really shift down so that the overall dispersion becomes negative. Okay? So these are called dispersion compensating fibers. So they have a profile something like this. Okay, so it's always negative. So these are dispersion compensating fibers. And so their index profile now looks even more extreme than this. So now the core is even smaller. Diameter is only about 3 micron. And the index contrast now is even larger, like 1.5 to 2%. Okay, so this is achieved by larger, for example, germanium oxide doping into the glass. Okay, so of course this doesn't come for free. Once you start doping at very high levels, you also start getting higher loss. Okay, so you can't just deploy very long lengths of this. But the nice thing is that, so you can see the magnitude. So first of all, it's negative of the conventional, but also the magnitude is much larger, right? So here, like let's say you have about 15 at 10 or 15 at 1.55. Here it's like minus 40 or something, right? So it's like 4 times larger in magnitude, which means if you want to compensate for the broadening, you only need 1/3 or 1/4 of the length of the conventional fiber, right? So you have some link of length L. To compensate for the broadening in that, you just add another dispersion compensating fiber of length L by 3 or L by 4 at the receiver. Okay. So these kinds of fibers are also more expensive because they're harder to fabricate with smaller cores and higher doping. Then there is another type of fiber called dispersion flattened fiber, which is used for WDM applications, wavelength division multiplexing. Okay. So nowadays, again, for increasing data rates, multiple channel or multiple different wavelengths are sent through the same fiber together, right? So, for example, almost this entire range from 1.3 to 1.6 is being utilized. So you can see that the dispersion is varying over that wavelength range, right? In the standard fiber. So different signals will have different types of distortion. So how do you overcome that? So you can design fibers which have a flat dispersion profile. So, for example, they have some. Okay. So over this telecom wavelength range, the dispersion is sort of flat, doesn't change much, and it's also very low. Okay. So typically like maybe 5 picosecond per nanometer per kilometer. So these are known as dispersion flattened fiber. Okay, and to achieve this kind of flat dispersion profile, you have to do now fancy things with the refractive index profile. So, for example, this now has a complicated refractive index profile like that. Okay. So, in the middle it's high, but then it actually goes lower than the cladding. There's a ring around the high index core which is actually lower than the cladding. Okay, again, all these games are being played to modify the waveguide dispersion such that we get an overall dispersion which is suitable for it. Okay, so this is about 0.7%. This inner core is about 6 micron, and then this outer band is about 9.5. Okay. Okay, so just to show you what sort of flexibility this waveguide dispersion gives us, right? So that we can easily design different fibers for different types of applications. Okay, so that ends our discussion on chromatic dispersion, right? So basically, the dispersion is happening due to the finite bandwidth in my signal, right? Coming from material and then waveguide dispersion. So the next topic is another source of dispersion, which is slightly different. Okay, it's called polarization mode dispersion. So as the name suggests, it's a dispersion mechanism which is actually coming from polarization effects. So far, we haven't considered any polarization effect. Right? We sort of assume that so the light is being guided in the fundamental LP mode, so it could be in some particular polarization, either X or Y. Okay. So some linear polarization which is sort of maintained along the fiber. But practically, what happens is that's not the case. Because basically for these really long lengths, kilometer scale lengths, right? The fiber cross section is not exactly the same. You can imagine that it's actually very difficult to maintain it, right? So these fibers are being made by like sort of heating this glass preform and then pulling it into thin strands, right? And so you can imagine there'll be tiny variations in the core, the cross section of the fiber, right? Both the size, shape, right, as along the propagation length for long lengths. Okay, and that what that leads to is sort of the fiber having slight birefringence, which means the two polarization orthogonal polarization components don't see the same refractive index anymore, slightly different because the core is not exactly circular everywhere. Okay, and that leads to mixing between the polarization components and actually distortion of the polarization as the field propagates. And that leads to, we'll see some broadening. Okay, so in terms of like the relative magnitudes, the intermodal dispersion that we discussed first, right? That's the highest in magnitude, right? So if you have multi-mode fibers with many modes, that's the dominant one. Then you eliminate that by going to single mode fibers, right? And then you're left with chromatic dispersion, material and waveguide dispersion, right? So that is the dominant one. Now let's say you compensate for the chromatic dispersion. Let's use the dispersion compensating technique that we discussed, right? So then now for long links, what you are left with is just polarization mode dispersion. Okay, so this is a smaller effect than both intermodal and chromatic dispersion, but it does have an effect when you compensate it for other dispersion, and especially if you're operating at high data rates, let's say over long fiber links. Okay, so basically what's the mechanism? So again, if you have a perfectly circular core, okay, so if you look at the LP01 mode, so because of the perfect circular symmetry, these two modes are degenerate, right? So this is the bipolarized LP01 and this is the X-polarized LP01. So they are degenerate for perfectly circular core. Just from symmetry. That means that the N effective for the Y polarized mode is the same as the X polarized, the propagation loss. So as I said, so now if you have a very long fiber, you can imagine there might be slight variations, right? Again, because remember how these are manufactured, or you heat a preform and then keep pulling them into small threads, right? So you can imagine, of course, there can be small, tiny variations, and actually the process has been perfected to a great degree, much better than probably is the most precise technology sort of engineered by mankind. But even you imagine, like, there are very tiny variations, like one part in 10 to the 6 or something. Okay, even that you'll see starts affecting once you go to lengths which are very long, right? Kilometers and tens and hundreds of kilometers. These very tiny small variations will start showing up. Okay. So again, these could be just changes in shape, right? So instead of circular, it's slightly compressed in one direction and elongated in the other direction, so it looks slightly elliptical. Okay, that ellipticity could be really small, as I said, like one part in a million, or okay, one part in at least 10,000. So very small, but still finite. And then also, as the fiber is laid under the ground or under the sea and like going over long distances, you can imagine there will be stresses on the fiber, right, due to twists and bends and whatnot. And these stresses also lead to Brier fringes. So there could be more stress in one direction than the other direction, right, which could lead to more compression in one direction with respect to the other, or just due to this photoelastic effect. Basically, once you put some strain on the material, it changes the refractive index slightly. Okay. So all these environmental factors also cause sort of non-uniformities in my cross section, okay, along the fiber length. So basically, what the cumulative effect of all these is that, so at any particular point in the fiber, you can sort of imagine the core not to be perfectly circular. This is highly exaggerated, right? The distortions are, as I said, very small. But just for our understanding, so imagine now the core looks like that. Right, so now you can see that these two polarizations, of course, will not have the same effective index. Right, so you can see that straightforward, for example, from the boundary conditions. Right, so this will have to satisfy boundary conditions here where the field is perpendicular, right? So the D will be continuous, whereas here E will be continuous. Here it's opposite. Here E is continuous. Here D is continuous. Okay. So these have to satisfy now different boundary conditions, which means that the effective index will not be the same but slightly different. Okay. So that is known as birefringence. Right. So you know a birefringent material is one where the two orthogonal polarizations don't see the same refractive index, and that is what is happening here in the fiber. Okay. So the fiber has now small birefringence. So basically, now these are not equal. Okay. So the birefringence basically the difference in the index between these two. Okay. So as I said, typically this value will be extremely small. Okay. Let's say, yeah. So 10 to the minus 7 to 10 to the minus 6 range. Okay, so you can see optical fibers are basically almost perfect, but there is a very small non-uniformity or imperfections coming along at various points in the fiber due to, again, these external factors and also this small manufacturing defects. But we'll see that even this value can have some significant effect. So now what happens, right? So at the input, so let's imagine we have some length of fiber here. Okay, so at the input here, so we don't know in which directions. So here basically we've called the direction in which the compression is happening as the Y, right, and the direction in which the elongation is happening as the X. But we don't know what those directions are, right? That depends on the environmental stresses and the manufacturing defects. So we don't know a priori which those directions are. So for some input polarization which is launched, we just launched some input linear polarization, right? So these two directions would be not, in general, not be along one, not be along the input polarization direction, right? So what I'm saying is, so these X and Y would be along some two random directions, and our input polarization would be along some direction which makes some angle with these two. Okay? And actually, for a long fiber, again due to twists and bends and also just from the manufacturing itself, these X and Y directions will keep varying, right? As you go along the length, the direction of the stress of the compression and the elongation will keep changing. So let's imagine some segment of fiber here, where at least the length is short enough, let's say, that these two axes, the direction is fixed. Okay? So the direction of the compression is fixed. So now my input polarization has components in both these, along both these axes. So, okay, so if I have a pulse, it has some power along both this Y and X. Okay, and now they have slightly different indices. So you can imagine that the power in these two components will now travel at slightly different velocities. Okay, so say let is some d. Okay, so let's this x-axis. So the direction in which the core is elongated, right? So that's x direction here. So now here nx will be larger, right? Because sort of the field is along the larger dimension of the core. Okay, So it's seeing more of the power will be confined in the core, whereas here less of the power will be confined in the core. So Nx will be greater than Ny, right? So X is known as the slow axis, and then Y will be known as the fast axis, because you know speed is c over n, right? So where n is larger, that's known as the slow axis, right? So that means this Y component will go faster. Okay, so it will go ahead of the X component. Okay, so now there will be some lag between the two, which we can call a broaden, right? So when we add up these two components, the total intensity will start looking something like that, right? Which gives me a broaden. So this relative delay delta tau So what will that be in terms of the birefringence, right? So the propagation time, let's say for each component, is the distance divided by the group velocity. So so we write this as group velocity is c over the group index, and the group index we know, we write this as, okay, so this will be for both the x and y components. So for x we'll have to take nx, and y we have to take ny, right? And they're slightly different. So then delta tau will be the difference between the x and y components, right? So from here you can see it's straightforward. So it will be the difference index here, delta n, and then we'll have d delta n by d omega. Okay, so you can see that for a segment of fiber of length d with some birefringence delta n, there will be a broadening delta tau given by this. Okay. So now this is for a segment of fiber which has constant birefringence. Why is it that x-axis is slow and y is fast? Because nx is higher. Right, so c over nx is smaller. That's why we call it. So in this case, we just chosen x to be it's just convention, right? You could have taken the slow axis as y and right. Yeah, there's no. But you understand that, so here is this case, this is the slow axis, right? If the elongated axis, that will be the slow axis. Okay, but you could equivalently take, like, for example, elongation like that, and then the y will be slow. So, okay, so here in our analysis, right, so we'll always denote. So as I said, as you go along the length of the fiber, these axes will keep changing, right? The direction of the compression and elongation will keep changing. But basically our axes are denoted such that always the elongated axis is denoted as x, that's the slow axis, and the compression axis is denoted as y. I'm trying to just I guess so it's not very intuitive to you guys, but so recall our discussion on slab waveguides. right? So for a slab, we had these TE and TM modes. Right, so what were TE modes? TE modes, like field polarized like that. Okay, so it's sort of like the field polarized along the long. So here, this is the extreme case where we have only confinement in one dimension. The other dimension is sort of free, right? But for a 2D waveguide, you can imagine. So for a 2D waveguide where one dimension is bigger than the other, the limiting case is the slab waveguide, where you just take the other dimension to be very large. Okay? So now here the field, the TE mode, the field is polarized along the larger dimension. Okay, whereas the TM mode has electric field polarized like that. Okay, and recall that the N effective or the propagation constant for the TE mode for some index M, or for our purposes we are discussing even the zeroth order mode. So TE0 was always less than the N effective for the TM0. Okay, recall just from the boundary conditions this came out, right? So it's the same case here. So imagine now, so instead of infinite slab, I don't have infinite, but now I have some finite dimension in the other direction also, right? So this is a much less extreme case of that. So the other dimension is also now finite, but bigger than the smaller dimension, right? So this is like the TE polarization here, where the field is polarized along the bigger dimension, whereas this one is field is polarized along the smaller dimension, like it looks like the TM one. Okay. So that's why this will have smaller N effective than this, just like this. Okay. Of course, if you want to convince yourself exactly mathematically, you have to solve for the modes. But physically, this argument holds true because this was coming from the boundary conditions. Okay. I hope that's clear. So whenever you have any kind of waveguide, if you have two polarizations, you can always say which one will have the higher N effective or the lower N effective, depending on if it's the field is polarized along the longer dimension or the shorter dimension. Okay. Right. So this analysis is for the for a small segment of fixed birefringence. So over a long length of fiber, basically we have to add up the effects of many such segments, where each segment has now a different slow and fast axis direction. Okay. So what the situation looks like is basically I have many, I can think of the long fiber as many segments of length d, each having a constant birefringence. By the way, for a practical fiber, this distance over which sort of birefringence is constant is typically about 10 meters. Okay. So if you take a standard single mode fiber, this distance d over which the birefringence width is typically about 10 meters. Okay. So now you know, of course, the lengths of fibers we're talking about are many kilometers or tens or hundreds of kilometers even. So then we consider basically many segments like these repeating after themselves. Right, so and basically the slow and fast axis. So let's say for this one it's like that, for this one it's like that. Okay, so slow, fast or XY, slow, fast. Okay, so okay, so basically the birefringence axis is randomly changing due to the random nature of the stress. So now you can imagine what's happening, right? So for each segment you get some sort of this lag between the polarization components. Now for the next segment, now you have to project the powers into the along the new axes, right? And then treat them as now independent components, which again acquire some lag. So now that could increase the broadening further, or it could actually make them come back together a little bit. Okay, so this almost looks like a diffusive process. Okay, so like in diffusion or Brownian motion, what happens is that like you have a particle getting kicked around, right? So it could go, for example, to the right, and the next kick could get another kick to the right, or it come back. It could get a kick to the left and come back, right? So it's like a random walk, right? So a particle starting from the center, right? It's getting random kicks, and so after some n steps, if you see where the particle is, right? So for this kind of diffusion motion, typically after n steps, the mean displacement from the center typically scales with square root of n, right? So right, this is, for example, how Brownian motion is modeled, and a lot of other random phenomena. Same thing you can think about here, right? So you have n segments, right? Each segment is giving me a sort of particular broadening, but the direction depends on the what is the angle of the birefringence. Okay, so the next segment could give me even more broadening if it's in the same direction, but if it's in a orthogonal direction or slightly different direction, it could actually lead to reduction in the okay. So for such type of diffusive, right? So what is again happening is I send some pulse here. So at the output there is some broadening. So this is some tau naught. Then here it's tau naught plus delta t PMD, right? And this delta t PMD is analogous to this displacement of the particle from the center, right? So the total length again is L, which we divide into n segments of length d. Okay, so of course n will be much bigger than 1, because again d is like 10 meters, where L is like many kilometers. Okay, so for this kind of diffusive process, basically what happens is that the mean square displacements, so in our case the displacement is the broadening, you add up all the mean square displacements over the n steps. Right, so imagine if all the segments were the same, right? Which means that the axes were in the same direction. That would be in one side, one fiber of the same birefringence everywhere. Then basically that will be like uh, a motion like this, right? It always keeps adding up in the same direction. This keeps broadening, broadening, broadening. So then you just add up the delta tau. Delta tau total will be just sum of the delta tau, right? So this kind of thing is known as ballistic walk. You just add up everything linearly. For this random case, it's more like a diffusive random, right? You can also think about it's like you have different error mechanisms, right? And if you have different independent error mechanisms, what is the total error that you have in your measurement is you add up the square errors from all of them, right? To get the total square. Okay. And this factor of 2 sort of takes into account that on average, like the next segment will either have the axis along the same direction so that delta t will increase, or in half the cases it will be in the other direction where delta t will decrease. Okay, so that's why 2 is correct. Okay, and so we have the expression for this delta tau for each segment from here. So you just plug that expression for delta tau for each segment here. So we get okay. So for each segment we have a delta ni and length di, but again without loss of generality, for long enough fiber, basically these variations are random, so that we can assume like length of each segment is the same, right? We've divided them into equal segments. And also the birefringence in each segment is the same on average. Okay, so as I said, so this is about 10 meters per single mode fiber. This is about 10 to the minus 7 to 10 to the minus 6 in that range. So that when we add up this group part also, the derivative, so this is typically about 10 to the minus 6 or less. Okay, so basically these are just constants now, right? And we have n of them. So we just have n times this constant. Okay, so we just take the square root for the broadening. So you can see that you get the square root of n dependence that we talked about for the diffusion. Okay. So of course we want our parameters to be in terms of like total fiber length or something. So again, we can put n equal to L over D. Okay, so here we put square root of L over D, so we'll get square root of L times square root of D. Okay, so we end up with this expression for the broadening due to polarization mode dispersion, which is some constant times the square root of the length. Okay, so you can see that this is slightly different from the other types of dispersion where the broadening went with linearly with length. Right, so here we have a square root of length dependence. And so if you put these numbers here, right, c is just speed of light, d if you put about 10 meters, this delta n plus derivative of delta n if you put about 10 to the minus 6, this coefficient here, okay, is known as d sub p. This is the PMD parameter. Okay, so you can see, so this is seconds, and here you have square root of length. So this PMD parameter has units of second per square root of meter. Okay, so it's usually measured in picosecond per square root of kilometer. And typically, so if you put these numbers, the typical value you get is about 0.15 picosecond per square root of kilometer. Okay, so now you can firstly see for the dependence is different, it's square root of length. Okay, so that first tells you that the other dispersion mechanisms will be dominant, right? Because they scale with length linearly. So only when you compensate for them, then you are left over with the PMD. Okay, and also the value you can see here is much smaller typically than the values we looked at for intermodal and then the chromatic dispersion. Okay, but again, for very long links where you compensated for the intermodal and, or if you don't have any intermodal for single mode fiber and you compensate for the chromatic dispersion, then the performance will be limited by this PMD. Okay, so you can see now, like for example, if you have very long links, hundreds of kilometers or 1,000 kilometers, then the broadening can be significant. So there are ways to, so typically people use some electronic means to compensate for polarization mode dispersion. So some digital signal processing techniques. Okay. So once you detect the waveforms into the using the photodetector into the electronic domain, then you add some phase shifts and try to sort of compensate for this delay and bring the broadened out pulses back together using some signal processing. Okay. One way you can sort of eliminate this polarization mode dispersion altogether is to use the type of fiber where, so recall fundamentally where this is coming from is basically these, we are starting from a circular core, perfectly circular core, right? Which is actually very difficult to maintain, right? So any small distortions lead to this small birefringence, which is randomly happening along the length, which is what is leading to this diffusive broadening, right? And also basically the polarization is not maintained. You start with some linear polarization, but now it has components along the fast and slow which keep varying, so polarization is sort of very scrambled, right? So the fiber is basically. So what one can do is actually use what are known as polarization maintaining fibers, which deliberately have a non-circular core. Okay, ENFs for short. So you deliberately have a fast and slow axis by design, but now you make the birefringence very, very large, such that small variations does not change. So here what the problem was, I didn't know where the fast and slow axes were along the length, right? That was the problem. If I knew, then for example, if you launch polarization either along the slow or fast axis, then it will be maintained along that axis, right? There will be no mixing. The problem was because these axes kept changing, I always had components in both of these, which led to a delay between. Okay, but so for example, you could have fibers where you design the core to be asymmetric. Okay, so for example, there is a fiber something which looks like it has three cores like this. So in the x direction, the effective index is higher, right? So this shaded region means higher index, so core region, and this is into. So now you can see this will be slow axis, this will be fast axis. And the simplest design could just be an elliptical core like that, right? There are more fancy designs like an oval core with a ring. Of course, the more fancy, so difficult it is to make. Okay, so this is the okay. So the point here is that delta n, which is the difference between the slow and axis, which is I know already defined and it's maintained along the fiber. Right, so you can imagine now any small variations. So the delta n here is much bigger, so like 10 to the minus 4 or larger. Whereas recall that this delta n from the random variations and the stresses were about 10 to the minus 6. Okay, so now any variations of 10 to the minus 6 order to this does not change my slow and fast axis. Okay, so I know in the beginning itself, at the input of the fiber, I know which is the slow and fast axis, so I can launch my input polarization along one of these axes and it will be maintained all along the fiber. Right? Any environmental stresses will not change anything much because they don't perturb this large birefringence. The perturbation is much smaller than the already existing birefringence. Okay, so the polarization is maintained and there is no broadening. Okay, so these are special fibers that one can use. But of course, in practical communication links, you can't replace the entire fiber optic network, all the single mode fibers with EMFs. Of course, firstly, they are very expensive compared to the standard single mode fiber. But for certain special applications in local area networks, you can use it. For typical long distance telecom networks, the compensation is done electronically using DSP techniques.